Water. Water is everywhere. It's in everyone. You're water. I'm water. Plants are water. Just look at each other and be like, yep, that's more water. Most reactions are going to involve macromolecules. Macro means what? Large. The micro means small. Macro means big. Big molecules dissolved in water. Water's super good at dissolving molecules because of its polar covalent nature. Water forms solutions. Now, a solution is simply a solute combined with a solvent. The solute is the substance that gets dissolved. The solvent is the substance that does the dissolving. If I was to take cupric sulfate, blue stuff, and add it to water, mix them together, I get a cupric sulfate solution. And you'll notice the cupric sulfate is gone. It magically disappears, except not magically, chemically. It is dissociated. It can recrystallize, that's absolutely possible, but for now it's gone. Kool-Aid, you've seen it happen. You take this big chunk of sugar and dye, you put it into a container, it sinks to the bottom. If you stir it up, it goes into solution. Water's not the only thing that can make solutions, though. Isopropanol. You take nail polish, if you have to get it off before you go to work because you don't want your students to see you with nail polish on. The way you do it, you take that nail polish, you put a nail polish remover, isopropanol, you put it on your nails, and it goes into solution so that when you take a cotton ball and rub against it, what happens? It comes off. It's now on the cotton ball, right? That's a solution that's not water. Sometimes water's the solvent, sometimes it's not. When water is the solvent, you form what's known as an aqueous solution. Salt water is an aqueous solution. What is the solute in salt water? Salt. And the solvent? Water. The end. Now, when you introduce solutes to water, you end up with these things called the colligative properties of water. Water, when combined with a solute, will shift some of its physical properties. And you've probably done this before in the past. If you guys ever cooked, I don't know, tried to boil water, and you add salt to it. Why do you add salt? It makes it boil faster. And flavor, apparently. Actually, yeah, no, most people say flavor. But the thing is, the big reason that you add salt to recipes, and we were adding salt for a long time, was because it changes the boiling point. If you were to add salt, if the normal boiling temperature is here, what's the boiling point of water? Okay, give me in Celsius, thanks. 100 degrees Celsius. If you were to add salt, that boiling point drops. So now you're cooking at it at a lower temperature. It boils faster. Now we're at, say, 96 degrees Celsius. Works on the other end of the scale, too. What's freezing point of water? So the freezing point is 0. If you were to add salt, what happens? It becomes lower. Now it's, say, -4 degrees. And that's good. That's why when we, it's getting ready to snow here, I assume salt trucks go around, drop salt on the road, or a brine solution?
Not really anymore. It's more
Sand?
Because chemically it messes with the environment.
Whatever, chemically it messes with the environment. They do it on the highways. So the idea is you put salt down, the freezing point, but also the melting point of the ice drops. So now the ice begins to melt instead at 0, it will melt at -4 degrees. That should explain why people get really, really upset when they don't see salt trucks going out and it's, say, in Celsius, -15 degrees out. They're like, where are the salt trucks? What happens? It won't do anything. People are like, why waste the salt? They have to, it's the mined ones. So there's a lot of different salts you can use. But the big thing is, no matter what salt you use, no matter what solute you use, the number of molecules per unit volume is going to impact how much of this drop is going to happen. Let me put it a different way. I can use salt. If I use a certain number of molecules of salt, it will reduce the boiling or the freezing point to like -4. If I use the same number of molecules of sugar, it will reduce it the same amount. So why is it that we don't use sugar on the roads and we use salt, which as we know is environmentally unsound? Sugar sticky. That's the reason, right? No, then there'll be ants and you don't want to deal with that. It comes down to cost. Sugar's more expensive. So those are colligative properties. In biology, organisms rely on these colligative properties to survive. The rock cod. The rock cod looks like glass, right? It looks like you can see through it. In the ocean, I'm going to die. In the ocean, you've got a layer of ice at the poles, and you got water underneath. The rock cod eats algae that's growing right up on that ice, and little copepods. It eats stuff right up along the ice. Now, that ocean right next to a block of ice is what temperature? Oh, this is hard. About what temperature? How about that? It's about 0? Yeah, give or take. Is it more or less than 0? Or is it exactly 0? It's got to be more than 0? Why? That's exactly it. Colligative properties, right? It's salt water, so the freezing point's lower. This is water here is actually like -1, -2. It's below freezing. That cod, if it had fresh water in it, would turn into a fishsicle. If you've played Mario Brothers, you know when you shoot an ice flower at a piranha fish? Yeah, and how it turns into a block of ice and floats up? That's what would happen to the rock cod. The rock cod actually avoids its enemies by living right up along the edge of the ice, because other fish can't get there or they'll freeze. And the way it does that is it creates a natural antifreeze. It produces a ton of solutes in its bloodstream. They get pumped out throughout it, so it doesn't actually, so its freezing point is lower than the freezing point of the water around it. The springtail here. Springtail is another Arctic organism. It survives in melt ice. The sun strikes the ice melts right on the top. A little bug comes and lays its eggs in that melt ice. That is as close to 0 as you can possibly get. Likely it's below 0 because of the solutes. But these springtails are pumping solutes through their blood too. And one of my favorite is the parasitic wasp, which by the way lives around here. I just saw one in my shed the other day. What the parasitic wasp will do is it will sting a caterpillar. And when it stings the caterpillar, it will do 2 things. One, it will inject it with solutes. Those solutes will allow the caterpillar to stay alive throughout the fall months. It will also inject it with its eggs, so that the reason the caterpillar, it's not like it's being nice and it's like, here, you can live now. It injects it with its eggs so that while this caterpillar is surviving through the winter or through the fall, the larvae are eating it from the inside out until eventually they burst out of the sides in like a horrible, I don't know. Did you guys ever play, when you played with Play-Doh when you were younger, did you ever do like the hair factory where they sort of, the hair comes out? Yeah, it does that, but with maggots. It totally is, yet awesome. If it stings a human. Luckily, these don't impact you. They only hunt caterpillars. They don't hunt humans. Yet. What? We absolutely, oh yeah, there's no good wasp out there. I'm a biologist and I have yet to find an ecological niche for wasps. Yeah, no, even those figs can be totally asexual. They do not need the wasp. So, yeah, no, because I grow fig trees too. And I'm just like, no, wasps, stay away. They can do that on their own. Now, the reason water has all of these cool properties is because of its polar covalent nature. Oxygen's highly electronegative, the hydrogen not so much so. So oxygen has a negative side, hydrogen has a positive side. It's got poles. And those poles will allow it to interact with different molecules in different ways. And it can interact with them in one of three ways. A molecule can be considered hydrophilic when it interacts with water. That is, it loves water. Philia means love. If you're an Anglophile, for instance, you love England. If you're xenophilic, you love aliens. If you're, I don't know, any other philias you guys know? What? Did you say necrophilia? You love dead bodies. Little things to know about Reagan. So, right, you got these philias. Love. These hydrophilic molecules are usually polar. They have a positive side and a negative side, or they're charged. They've got a positive, they're positive, or they're negative. So in order to dissolve them, what will happen is water molecules will surround the poles, the polar parts of the molecule. Here we've got a whole bunch of negatively charged hydroxyl groups. Water is being attracted to them, and it will pull them apart. Now, this picture is wrong, and I always leave it up here. I do it on purpose. It's not because I really forget after class to go and change the picture. This picture is wrong. What I just told you was the way this works is these water molecules are going to be attracted to the charged parts of a molecule. So why is this picture wrong? That's exactly right. The negative side of water is attracted to the negative hydroxyl group. And that's not the way it works, because what would happen if I had a negative and a negative? They repel. So I screwed that up. Should be the other side. Should be the hydrogen sides flipped around. It would be. It's just all PowerPoint. I can move things around. Another type of molecule are hydrophobic molecules. Phobia. Okay, Reagan, redeem yourself here. Are there any phobias you know of? Seriously? Fear of dead people. Okay, that works. Necrophobia. Any other phobias? Arachnophobia. Okay, there's one. Fear of spiders. Acrophobia. Fear of heights. What's agoraphobia? Fear of people. I think we all have that one. I think we're just like, or it's just we don't like people. Claustrophobia? Claustrophobia. Yeah, I thought clusterphobia, and I was like, fear of clusters? Claustrophobia, yeah. People are, okay. So there are a lot of fears out there. In this case, it's hydrophobia. So hydro is water, phobia is fear, so you fear water. These hydrophobic molecules have what are termed nonpolar binding sites. That is, they don't have, they're made up of molecules that have similar electronegativities. Hydrogen and carbon have very, very similar electronegativity. They share electrons evenly. So there's no positive or negative sections of this molecule. Oil is a hydrophobic molecule. It's a hydrocarbon. Those hydrocarbons tend to be hydrophobic. They repel water. So if I was to take oil and water and put them in together, what would happen? They don't mix. You make you take vinegar and oil and you shake it up and you make salad dressing, but you have to always shake it up in order to sort of combine them, but they never truly become a solution. They never become homogeneous. And the last type of molecule is the amphipathic molecule. I love amphipathic molecules. Amphipathic molecules have both polar domains and nonpolar domains. So they have this side up here that's got a plus and a minus. They're polar up there. But down here, lots of carbon and hydrogen, so they're hydrophobic. So you got one side that loves water and one side that hates water. Amphi means both. Right, so it's got both feelings. Pathos. You guys ever seen a two-headed turtle? Okay, so there's this two-headed, I used to live near Greensboro. There's a two-headed turtle in the Greensboro Aquarium, and I love watching him because one of the turtle heads, and they think independently, likes to swim. The other one likes to be on land. So it's great because one controls this half of the body and one controls this half of the body. And you can see it's like, I'm trying to get to the water. And this little head is pointing that way like, I want the water. And the other one's like, no, land. It both loves and hates water at the same time. And you see an orientation. You always see the water-loving head facing this way and the water-hating head facing that way. It is so neat. And I actually managed to get a field trip for my students down there once because I was like, we have to learn about this and see a two-headed turtle. So when interacting with water, if we were to have this structure, that structure, by the way, is a phospholipid. We'll learn about those in the next lecture. You've got this part up here that's facing water. This part faces away. But when there's water down here and over here and also over here, you have to have a bunch of these lipids, phospholipids, these amphipathic molecules, so that the heads all orient toward water and the tails away. This forms a structure called a micelle, or it might form bilayers. But this is sort of rudimentary how you originally got the membrane surrounding cells. Just chemicals reacting to the environment around them. So you've got hydrophilic, they love water, hydrophobic, they hate water, they're repelled by water, and amphipathic. Hydrophilic ones are usually going to be charged. They'll have poles. Hydrophobic ones do not have poles. They're uncharged. And amphipathic ones have one part of them that's charged and one part that's not. That's actually a really interesting way of putting it, because I would say no, water is none of them, because water is what everything is. Water's pretty much what everything's compared to. It's the standard of comparison. If I was to put water in any of the categories, I would say it's hydrophilic. It loves itself. You say me too? I just love me. Water has a bunch of important properties. It takes place in lots of chemical reactions. It's incompressible. You can't squeeze it. It removes waste from organisms. It evaporates at room temperature. It has a high specific heat. And it forms droplets that are cohesive. So first off, we did not talk about this in lab, and I really want to stress it because this will come up again and again and again and again. Water takes place in a lot of reactions, and there are two big kinds of reactions I need you to understand. Hydrolysis reactions and condensation reactions, or dehydration synthesis reactions. So first off, hydrolysis. Look at the words. Hydro, water. Lysis means to break down. So in this case, you're using water to break something down. You're taking a macromolecule, and in the presence of water, it splits the macromolecule. That's really interesting. So you get, and then you got condensation reactions. Condensation reactions will take two reactants, put them together, and water's released. So you've got dehydration. You're losing water in the process. It's being released. But you're building a macromolecule. You put them together and water's released. Yeah. Yes? So hydrolysis is going to break a molecule apart using water. So here we've got that. Here's a chair, and then here's another chair. These two chairs are put together. They are a macromolecule. Does that make sense? They're a big molecule. Annie, is this water? Yep. All right. How do I get into it? Right there? All right. So, there. Water's added, and they break apart. Make sense? Awesome. Okay. Now, here I've got two molecules. One has some of the water, one has the other part of the water. I remove the water. Oh, that's going to be bad for somebody. And they get put back together. Now it's a macromolecule. That is a dehydration reaction because I'm removing water. It's dehydrating. Or it's also called a condensation reaction because I've taken two molecules and condensed them. Make sense? So hydrolysis and condensation. Hydrolysis will split, condensation will build. That's going to come up a lot. Oh, good. The one the teacher's going to sit on does not have the water. And this one's just up here anyway, so whoever sits in this chair, they're on their own. It's okay. Don't worry. It's my class that's coming in next. I'll explain that one of you guys did that. All right, so you got water's incompressible. You can't squeeze water. That's super weird, right? Because you can take oxygen, all of the oxygen in this room, squeeze it down and put it into a tank. You squeeze it down even more and it becomes solid. You can't do that with water. Literally, if you fill this room with water, you can't squeeze it anymore. Once it hits its most dense, you can't get it any tighter. And it comes back down to the idea that water, the hydrogen bonds in water are adding additional support. So plants use this property. Most of a plant is water. So they fill their cells with water and they can't compress it, so that's where they get the strength and rigidity. Water is used to eliminate waste. Your body has to take uric acid, urea, which is not really terribly water soluble, and get it out of your body. The only way it does it is it takes the crystals and it puts it into water, super concentrates it into urine, and you pee it out. If you can't get rid of it, you die. I mean, the toxins build up. In case you didn't know, these are urinals. I mean, I know some of you are like, whoa. They are located in the men's room. Normally, there aren't this many of them. There's etiquette to it. If the door's right over there, it's in case you ever needed to know, you walk in, where's the first one you go to? That's exactly correct, Annie. Well done. Well done. The one on the very end. Second person walks in the door. Where do they go? That's right, this end. There's much space in between. Third person walks in, goes in the middle. That's easy. Fourth person, it gets harder. That's exactly the right answer, Ray. That's the advanced way of doing it. You wait. There's always a stall. You could go to the stall. There's always a sink, I guess. I mean, there's all sorts of places. But okay, let's be honest. How often is it that there's 5 men in a restroom at one time?
And not only that, there are no dividers.
And there are no dividers. Yeah, it's like a trough. There's a code, and you must follow the code. Water evaporates. At room temperature, so right now at room temperature, water molecules will break away from each other. What is holding water molecules together? What kind of bonds? Hydrogen bonds, and they're really weak. Little random molecular energy added to that water will break the bonds and allow it to float away. So here's the deal. When you get hot, you sweat. Don't try and deny it, you do. What is sweat made of? Not trying to trick you. Water. And salt. You know it's salty because at some point you've gotten sweat in your mouth. It may have been your sweat, it may have been someone else's, whatever. There is salt in sweat. Colligative properties, right? What happens if you add salt to sweat? It's going to evaporate easier. So now we've got this stuff that evaporates very quickly. All right. Exactly. What happens then, all right, you're adding energy, kinetic energy, energy of motion to these molecules, these water molecules that are on the body. What happens to any molecule when you add energy to it? The electrons speed up, the electron cloud expands. So now this molecule has some energy to it. It's got excess energy from that heat, or from your body heat, and then it's got enough energy to break that hydrogen bond and float away. And as it floats away, it takes that energy with it. So as you get out of the shower and you were covered in water, what do you feel? Cold. Cool. Right. And in lab, we looked at what? Isopropanol and water. One of them evaporated faster than the other. What happens when you put alcohol on your arm? It feels really cold, right? It's because it's evaporating so quickly, taking that energy, that excess energy with it. Water has a high specific heat. It takes a lot of heat to heat up a body of water. It's because the specific heat of the water is so freaking high up there. Think about simple thing first. A pot of water. Okay, you put a pot of water on the stove. What gets hot first? The pot or the water? The pot. Don't touch the pot. This is good advice across the board. That's because metal has a very low specific heat. Water has very high specific heat. It takes a lot of energy to heat up a little bit of water. It takes a long time for water to boil. Now, if you had just a little cup of water, you put it in the microwave, it takes what, like 5 minutes to boil. You take 3 quarts of water, you try and do the same thing, it takes a lot longer. And transitioning over to baby pools. You guys ever played in a baby pool before when you were an adult? Yeah, because that's what you do. So it's the idea, you've got this pool. You fill it with cold water, and you sit in it because it's a hot day and you're poor and you don't have like access to a pool or something like that. So you sit in it. What happens to the water very quickly? It boils, and then you die, and you didn't even realize you were in there. It doesn't boil, but it does get hot very quickly. That being said, if you were to go to a lake, large body of water, you sit in it all day long, you're not going to distinguish much of a temperature change. In fact, heating up and cooling down a lake takes an insane amount of time. The bottom of the lake tends to stay cool year-round, 4 degrees Celsius roughly. It's the top of the lake where you get a change in temperature. You can heat up the whole lake. You can cool the whole lake down, but it takes a long, long time. This leads to actual local temperature stability because water doesn't just exist in liquid form, it exists in gaseous form, right? So if you live down over by a coast, or say in Virginia, it's humid. It's really freaking humid. Always. Your hair's noticed. Does that make sense? It's always humid. But that being said, that humidity leads to the temperature staying roughly the same between night and day. It's 60 degrees, in real life, right? It's like 80 degrees during the day and 75 at night. There's not much of a difference. You'll notice that when it's raining during the day, it's going to be pretty much the same temperature during the rain during the day as it is at night. It's because of that water. Water has a very, very high specific heat, so it's so humid out, it's going to maintain that temperature for a long time. If you look at a desert, now deserts are known for being what? Very dry, very cold at night, and very hot during the day. Because they are so dry, the water cannot trap the heat. So you're losing heat and gaining heat very, very quickly. Now it's sand. Sand has a very low specific heat. It heats up and it cools down fast. You've been to the beach, right? Yeah. You go out to the beach in the morning, early in the morning too. You go out there and you're like, I see the water. It's 30 feet away. I don't need flip-flops. I can just go right for the water. And you're like, step, step. And it's that second step where you're like, oh, this is crazy hot, but I can't turn around or I'm going to look weak. Step, step. And then you're like, oh, God, I'm dying, but I still have to look cool. Right, but you start walking a little faster until you're like 10 feet from the water, and you're like, oh, God, just let me in. It's because that sand has a very, very low specific heat. It heats up fast, but the water, oh, the sweet, sweet relief of that water, it's cold still because of overnight. The sad part, though, is when you're like, it's so hot in the sand, I'm just going to dive right into the water. And then it's freezing. Yeah. Water has a high specific heat, so it's going to cool down and heat up very, very slowly. Water molecules form droplets that are both cohesive and adhesive. They stick to each other. That's cohesion, sticking to each other. And that allows for the formation of these drops. And then adhesion, they stick to objects that are not polar. And of course, water expands when it freezes, and you get ice floating. Now, not all of ice floats above the water. Some of it still dips below the water, icebergs and such. Titanic, you've heard of it. It sank because they underestimated the size of an iceberg. They're like, don't worry, it's just that bit sticking out over there. It's not, among other things. The expansion of water when it freezes means that the bottom of the sea never freezes solid. It never actually even gets close to that. It sits at 4 degrees Celsius. It's higher up where you might freeze, and that allows for a zone where life can live. So those are the important properties of water.